Today I'm going to be talking about the history of the Jeffcott rotor. Starting in the late 19th century, rotating machines became extensively used in engineering and industrial applications. As a result, analysis of rotor dynamics became a subject of great interest around the same time. W. J. Rankine in 1869 performed the first published analysis of a spinning shaft. He analyzed a simplified 2 degrees of freedom model, which consisted of a rigid mass whirling in orbit with an elastic spring acting in the radial direction. His model predicted that beyond a certain speed, referred to as the whirling speed, the shaft will deflect radially and whirl around in the bent form. In fact, if the speed is increased past the whirling speed, his model predicted a limitless increase in radial deflection of the shaft. He postulated that above this speed, no matter how balanced the system, shaft operation was impossible. As it turns out, his model was incomplete. However, Rankine did introduce whirling to rotor dynamics, which refers to the movement of the center of mass of the rotor around the shaft. Stanley Dunkerley in 1895 was the first to use the term critical speed in a study of the vibration of shafts loaded by pulleys. Critical speed is a speed above whirling speed at which the shaft regains operational stability. The observation of this phenomenon directly contradicted Rankine's predictions. A German engineer, August Foppel, used an undamped rotor model to show that an unbalanced disk would whirl synchronously with the center of mass facing out when the rotation was subcritical, and with the center of mass facing in when rotation was supercritical. Effectively, his analysis explained why operation above critical speed was possible. A Swedish engineer, Carl de Laval, experimentally demonstrated this phenomenon by running a steam turbine at supercritical speed. Finally, Henry Jeffcott was commissioned to resolve the discrepancies between Rankine's prediction and de Laval's demonstration. At this time, Foppel's analysis was unknown simply because the journal he published in was little known in the field of rotor dynamics. Jeffcott's analysis was nearly the same as Foppel's, a massless shaft supported by bearings at either end and carrying a mass at its center, with that center of mass being offset from the central axis of the shaft. Although he never referenced it, presumably because he wasn't aware of it, his work did build upon Foppel's prior work, extending the analysis to include external damping. So although Foppel was the first to model it, the rotor model is more commonly known as the Jeffcott rotor.